This is lecture 2E for Calculus 1 on the intermediate value theorem. The intermediate value theorem says that if a function is continuous on a closed interval, here I'm calling it x1 and x2, get the pointer here, or the highlighter. Okay, the function is continuous on the closed interval x1 and x2. Then it takes on all values between its value at x1 and its value at x2. This is just a statement of continuity, right? And in particular, if the function is positive at x1 and negative at x2, then somewhere between x1 and x2, it takes on the value 0. A value of x where the function is 0 is, of course, a root. This means that if I can find two values of x, x1 and x2, where the function is positive, and if it's negative at the other value, somewhere between x1 and x2 is a root, is a value of x that would send this equation to 0. Since finding roots is one of the big problems, especially with polynomials, this intermediate value theorem will give us a numerical way to do this, to find these roots. Here's a graph of the arc sine, and let's just look at this closed interval between minus 0.6 and plus 0.6. Okay, arc sine is continuous between those two values. That means that it's going to take on all values between its value at plus 0.6 and its value at minus 0.6. And in particular, somewhere, because these are positive and negative, somewhere between negative 0.6 and 0.6, the function will cross the x-axis and a root. And that will be the root. Okay, in this case, the root would be x equals 0. So if I can find two values of a function, of a continuous function, one where it's positive and one where it's negative, I know that a root is hiding between those two values. In this case, it's very symmetric. Realize you'll be solving many of these functions on a computer, and the computer doesn't, although it can draw a graph, doesn't understand a graph the way that we do. So here's the procedure for using the intermediate value theorem for finding a root. First, you have to have two guesses. You have to guess the x1 and the x2. You have to find them in some way. And you have to find them in a certain way that the function's positive at x1 and negative at x2, or vice versa. It doesn't matter. Okay, so you've got two values. We're going to say x1 where the function's positive and x2 where the function's negative. By the intermediate value theorem, I know that hiding between x1 and x2 is a root. So to find it, what I do is average x1 and x2. That's what I'm doing right here. And get a new value of x. So I look at some x between x1 and x2, and I pick that x based on the average. Okay, this is a continuous function. It has a value there, so I evaluate the function at this new average. If it's greater than 0, then I reassign x1 to be x new. If it's less than 0, I reassign x2 to be x new. This way I've created a smaller interval, and I know that the root is still hiding in that smaller interval. So I keep repeating steps 1, 2, and 3. Every time you repeat steps 1, 2, and 3, that's called an iteration. I keep making enough iterations until I decide that either I'm close enough to the root, that the answer is so close to 0 that any difference is probably due to the limits of the computer, or I look at the difference between x1 and x2 and say I'm close enough in that interval. We can use this intermediate value theorem and this idea to find roots of any polynomial or any algebraic combinations of continuous functions. Polynomial like that, you're not going to solve analytically, because there's going to be a lot of roots. Some, of course, could be complex. But you can use the intermediate value theorem to go after these roots. Same thing with a function like this. You've got two continuous functions, one raised to a power, and then you have a linear combination of continuous functions, so you can use the intermediate value theorem there. Another way that it's used is to find values for irrational numbers. So you want a value for square root of 2 or the square root of 3 or pi. Here's how you do this. You set up a function for which that irrational number would be a root. So here I say if f of x is x squared minus 2, then the square root of 2 is a root of this function, because at square root of 2, f of x is 0. The same way, if I say f of x is x squared minus 3, the root of this equation is the square root of 3, or here, obviously, a root is pi. I demonstrate this, this method by trying to find a value for the square root of 2. So I set up my function, I let f of x be x squared minus 2. So now I have a continuous function. I know the root is the square root of 2, but I don't know the value of the square root of 2. Or I'd rather like to find the value of the square root of 2. So I pick two values, x1 and x2, so that the function is negative at one of them and positive at the other. All right. So I know that between 1 and 2 is the value of the square root of 2. Okay. In step 1, I take the average. Now, note here that I'm taking the average of the x's, not an average of the y, an average of the x's. So I look for another x value by averaging 1 and 2, and I get 1.5. I take this new value and I evaluate the function at 1.5. If the value of the function at 1.5 happened to be 0, I'd be done. I would have found the root. But that's usually not the case. In this case, it's greater than 0. So I reassign my upper limit to be 1.5, and now I have a new interval, 1 to 1.5. You see, this interval between 1 and 1.5 is smaller than the original interval of 1 to 2. But I know that the root is now bracketed in this smaller interval, and now I continue this process. So here is the result of 9 iterations. I start with an interval 1 to 2. Okay, I know the root's there. I find that the average, the midpoint in that interval is 1.5, and I evaluate the function there, and I find out that it's positive. So I reassign the 2. Now I have an interval 1 to 1.5. I look in the middle of that interval, which would be at x of 1.25. I find that the value is negative. So I reassign the lower endpoint. Now I have a smaller interval, 1.25 to 1.5. I look in the middle of that interval, which would be the point 1.375, evaluate the function, find it's negative. So again, I reassign the lower endpoint. So I keep doing that. Here's what I end up with at 9 iterations. 1.4125 for the lower endpoint, 1.41976 for the upper endpoint. Halfway in the middle of that is 1.415625. Okay, what is the actual value of the root? The actual value of the root is 1.4142135. If you look down these list of numbers, you see that the function did get closer and closer to 0. And at some point, of course, you just stop. Obviously, such a method is very suitable for a computer. The computer would have no trouble taking quite a few number of iterations, but there is a limit to the accuracy of the machine that you're working on, and at that point you would stop. Here's a graph of the process. I started out with the interval 1 up to 2, and I knew that somewhere in there the root was hiding. Okay, after I take these averages and reassign the endpoints, now I've got a narrower interval. See the one between the stars? I keep going with these iterations. Of course, I haven't shown every step, but now I have a smaller interval. For example, the root would be bracketed between those two open squares, and then between those two those triangles, those black triangles there. You can see how we're just kind of scrunching down on the root, and that is a method of using the intermediate value theorem to find roots of equations, and in particular to find values for irrational numbers.